Good morning or afternoon or whenever you're watching this video. So this is a short video lesson. I want to talk about the notion of probability as area. This is going to be an important concept when we do the normal distribution and normal probability problems coming up. So let's just look at for a second, if I said, consider the experiment rolling a die. It's so light, I don't know if you can see that. I'll use black. Rolling a die. There are 6 possible outcomes, right? 1, 2, 3, 4, 5, 6. If we were to graph that as a frequency graph, it would look something like this. Let's say rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, and then rolling a 6. And let's just say that this was the frequency of each of those things happening. Let's say we roll the die over and over and over multiple times, maybe even 200 times. Well, if we rolled the die 200 times, what would the frequency with which these 6 things would be observed in a perfect world? But 200 times is a lot of data points. So most likely it would look like this if we graphed it. The frequency of 1s would be about that many, which would be the same as the frequency of getting 2s, frequency of getting 3s, getting 4s, getting 5s, and getting 6s. That's sloppy. But you get the idea. All of those things are equally likely, and if we did it enough times, 200 times, can you see this? If we did it 200 times, most likely, it could be little exceptions, but most likely, each of them would occur the same number of times. So I don't know what number that would be. I guess 200 divided by 6, but the percentage would be the same. And it would be about 16, 17%, around 17%. And then they all should add up to 1. 17 or 16.66 repeating. So all of these probabilities, all of their relative frequencies, when added, would be 1. The entire everything that happened. So let's think about this then. I could do the probability of rolling a 2 or a 3. I can picture the probability of rolling a 2 or a 3 as really the sum of the area. Oops. The sum of the area in both of those rectangles. So if we added up the area, we would get the probability, which would be, about 34% chance, that is, so 0.3400, about. How did I get that? Well, they're all about 16, 17% chance. So 2 of them, any 2, we would add up the area, and the area under that graph would be the probability. Now I'm saying this because what happens when the graph is funkier? You do the same thing. The whole total area has to equal 1. The total area has to equal 1 of the whole blue rectangle, because that's every possible thing that can happen. And no matter how slight the chance, all of the percentages added up have to come out to be 100%. So we're not interested in how many times out of 200, we're interested in the percent. What is the percent of times that happened? Well, all of them have the same frequency, the same percentage of the whole in the probability problem. So you could say the area of the total blue rectangle is everything that could possibly happen, which is 1. Probability area. By the way, if all the probabilities are equal, like this example is called a uniform probability distribution. You see that red? Uniform probability distribution, because everything has the same probability of happening. If we did one for flipping a coin, probability distribution for heads or tails would also be uniform. And guess what? It would add up to 1. So if we did this board, can you see this board? Probably not. So if we did the experiment flipping a coin over and over, I need a darker marker.
A darker marker.
Try the black one. If we did the frequency graph, there's only 2 things that can happen: heads or tails. And both of them on the frequency graph, if you can see that, would be 50% of the time. Again, the total area is 1. Because it's another example of a uniform probability distribution. Okay. Pause. I'll be right back. I gotta erase this board. So we're continuing. The eraser was messy. Back to this board. So now let's talk about, remember when we rolled 2 dice and added the 2 dice together? There are lots of things that can happen. You could get a 2, you could get a 4, you could get an 8, all the way up to 12. But they're not all the same probability. So that is not a uniform probability distribution. It turns out that graph looks something like this. Experiment. The sum, I'm abbreviating, the sum of 2 dice. That graph what's the very smallest thing you can get if you roll 2 dice and add them up? 2. 1 and 1. So that's going to be one of the outcomes. You could get a 3, but there's going to be more chances of getting a 3. You could get a 1 and a 2 or 2 and a 1. So this probability is just 1. Not 1, I'm sorry. That probability, there's only one way that can happen. So it's 1 out of 36. 3 can happen 2 ways. You can get a 2 and a 1 or a 1 and a 2. To get a sum of 4, you can get a 3 and a 1, a 1 and a 3, or a 2 and a 2. 3 ways. And so forth. Now, When you roll a 5, again, that's going to be one more way. A 6 is going to have one more way. And then it turns out a 7 has the highest chance of happening, because there's lots of ways to make a 7. You could have 1 and a 6, 6 and a 1, 2 and a 5, 5 and a 2, 3 and 4, 4 and 3. 6 different ways. 6 ways out of 36 possible things that can happen when you roll 2 dice. That's a percentage. I don't have my calculator. The point I want to make is the same number of ways you could make a 6, you can make an 8. The same number of ways you can add up to be 5, you can make 9. The same number of ways that you can add up to get a 4 is the same number of ways you can get a 10. Not too many ways. And the same number of ways you can get an 11 is the same number of ways you can get a 3. How do you make 11? 2 ways. 5, 6, 6, 5. That's it. And then finally, the number of ways you can roll and add up to 12 is one way. 6 and 6. That's it. Exactly the same number of ways as rolling a sum of 2. Look at that. Look familiar? You betcha. It's a bell curve. So in probability theory, we sketch this out so it looks something like that. That is called a normal distribution. Or, as most people call it, the bell curve. Many, many, many things in life are bell curves. So the mean is the one that happens the most. Remember mu? That's the mean. In probability and statistics, mu is 7. Now there is a standard deviation. I don't know what it is, but it's around here. One standard deviation from the mean. I'm not going to get too far into that. I just want to make the point that this probability distribution graph is not uniform. In fact, it's a bell curve. But guess what? Area is still the same as probability. So if I said, listen carefully, if I said, what's the probability of rolling a sum less than or equal to 5? That's so light. I hope you heard it. I'm trying to find a dark marker here. The probability of having the sum of the dice less than or equal to 5 is the same as the area underneath the distribution curve from 2 to 5. So this shaded region, the area of that shaded region is the probability. And there are going to be ways to find out the area under a bell curve. We're going to use a calculator. We're going to use tables in the back. There's ways to do this. There's plenty of ways to find out what the area actually is. In our case, we could add them up. They're not too hard. But other probability problems that are normal distributions will be hard to add up, because there may be hundreds of different things that could happen, not just these 11 things. So that's what I want to talk about. Probability is the same thing as area under the frequency distribution graph. This is the frequency. That would be in percents. The area under the curve. We can do this out and actually get a number. I'm not as concerned about the actual number. The area under the curve, less than or equal to 5, is the same thing as the probability. And again, the area under all of them equals 1. Same, because it's probability. So I should say that.
Maybe the red's darker.
We're going to need this information when I come back on Wednesday because we're going to talk about the normal distribution in much more detail, the bell curve. Your job right now is to remember that the area under the curve is the probability. I hope you can see this dark one. So the total area under the curve is the same thing as the total probabilities of everything that could possibly happen. All those percents have to add up to 100%. That's the same as saying the area under every probability curve is 1. Whether it's a simple example like dice, 50 and 50 add up to 1, or it's these probabilities, which is many more different numbers, they have to add up to 1, the total area under the curve. The area is the probability. That's the lesson. Area, probability. Did you get that? Take a minute. Write down everything you need to write down. I'll zoom in. Signing off. Bye.